Somewhere, inside a dying giant star, the last useful fire has gone quiet. The outer layers still shine, still swell in the dark, still look from far away, like a star that has time left. But deep in the center, where iron has gathered like ash at the bottom of a furnace, gravity begins to take back everything fusion once held apart. The core does not fall like stone. It falls like a whole world, suddenly remembering that nothing beneath it is strong enough to remain open. Before this slow journey moves inward, take a moment to make the room softer around you. If these deep space stories help you rest, think, study, or drift towards sleep, a quiet like, a subscribe, or a share helps this channel keep making long, calm journeys through the universe. And if you feel like leaving a small note, write where you are listening from and what time it is there. Maybe it is late at night beside an open window. Maybe the room is dark except for one small screen. Maybe a fan is turning somewhere nearby, steady and low. Settle into whatever position feels easiest. Let the shoulders loosen. Let the light fade a little. Nothing here needs to be solved all at once. The star has been moving toward this ending for millions of years, and the story can move slowly too. Beyond the quiet of the room, the iron core grows heavier. Around it, shells of older fuel still burn, each one thinner, faster, less able to answer gravity. For a long time, the star has lived by balance. Now that balance is beginning to fail. And in that failure, one of the smallest laws in nature is preparing to hold back one of the largest forces in the universe. Long before a neutron star appears, there is only a star that burns too quickly. It begins with a kind of brightness that cannot last. A blue-white furnace held together by gravity and by the heat rising from its own heart. From the outside, it may look steady. Light leaves its surface and moves out into the dark for years, centuries, or longer before it reaches any eye that can receive it. But inside the star, nothing is still. Matter is falling inward under its own weight, while energy from fusion pushes outward through layer after layer of plasma. The star survives because these two motions, inward and outward, are almost perfectly balanced. It is not peace, it is a pause. A star like this is born with far more mass than the sun. It may contain 8 times the sun's mass, or 15 times, or 20 times. That mass changes everything. Gravity presses harder. The core becomes hotter. Fusion runs faster. The star shines with a force that makes ordinary starlight seem quiet by comparison. A small red dwarf can burn gently for trillions of years, using its fuel with almost impossible patience. The sun will live for billions of years before its center changes beyond recognition. But a massive star spends itself quickly. It is large enough to become a factory of elements, and that gift comes with a short life. At first, the process is familiar. Deep in the core, hydrogen nuclei are fused into helium. The star is turning the lightest element into the next one, and in the change, a little mass becomes energy. That energy does not simply appear as light at the surface. It begins in the deep interior, where particles move in a dense, hot sea, colliding, scattering, absorbing, and releasing radiation again. The energy works its way outward slowly. It pushes on the matter above it. It gives the star an internal pressure, a broad, outward support that resists the pull of gravity. Gravity never stops pulling. Every part of the star feels the attraction of every other part. The outer layers fall toward the center in the same quiet way that a stone falls toward a planet, except here the falling material is plasma, and the planet is the star itself. Against that inward pull, fusion provides heat and radiation. For most of the star's life, the balance holds. Gravity tries to make the star smaller. Fusion keeps it open. That balance is called hydrostatic equilibrium, though the name is less important than the image. A star is not a solid object. It is a self-gravitating ocean of gas and light. It keeps its shape because pressure increases with depth, because the deeper layers carry the weight of everything above them, and because the core continues to release energy. If the core produces slightly more energy, the star expands a little. Expansion cools the core, and the fusion rate eases. If the core produces slightly less energy, the star contracts a little. Contraction heats the core, and fusion rises again. For a long time, the star corrects itself without thought or intention. It breathes through physics. The first long chapter is hydrogen burning. In a massive star, even this long chapter is brief by cosmic standards. Hydrogen disappears from the core, while the outer layers still look bright and whole. The star does not announce the change from the outside. It does not suddenly go dark. But in the center, the supply of hydrogen that once held gravity back begins to thin. Fusion slows. The outward pressure weakens. The core contracts. This contraction is not a failure yet. It is the way the star finds the next step. As the core shrinks, gravity does work on the matter inside it, and the temperature rises. The helium left behind by hydrogen burning is packed closer together. At a high enough temperature, helium begins to fuse into carbon. Once again, energy is released. Once again, pressure returns. The star settles into a new balance, hotter and less patient than before. Around the core, the rest of the star responds. Hydrogen may still burn in a shell outside the helium-burning center. The outer layers swell. The star changes color and size. It may become a supergiant, with a body so large that if placed at the center of the solar system, its outer atmosphere could reach far beyond the orbit of the inner planets. Yet the huge size can be misleading. The outer envelope is thin compared with the density of the core. The visible star grows vast and red, while the center becomes smaller, hotter, and more crowded. Helium burning lasts a shorter time than hydrogen burning. The star is moving through its fuels, as though each one opens a door that leads to a smaller room. When helium in the core is spent, carbon remains. The core contracts again. The temperature rises again. Carbon begins to burn. It fuses into heavier nuclei such as neon, sodium, magnesium, and oxygen. The star finds another balance, but this one is more temporary than the last. The rhythm is now set. A fuel runs out. The core contracts. The temperature climbs. A heavier fuel begins to burn if the star is massive enough to ignite it. Each new stage demands a higher temperature than the one before it. Each new stage lasts less time. The reason is not only that the star is running out of possible reactions, it is also that the energy released by later fuels is less efficient, and the core loses energy in ways that ordinary starlight does not reveal. Neutrinos carry energy away from the interior with little resistance, slipping through the star almost as if the star were transparent. The deeper the star goes into its final burning stages, the more of its energy escapes by these nearly invisible particles. Carbon gives way to neon. Neon gives way to oxygen. Oxygen gives way to silicon. The names can sound like a list, but inside the star they are layers of fire, each one written by pressure and heat. The center is always the most advanced part, because it is hottest and densest. Around it, shells burn earlier fuels. A shell of silicon may surround a growing core. Beyond it, oxygen and neon burn in another shell. Further out, carbon burns. Further still, helium and hydrogen continue their older work. The star becomes stratified, not neatly like stone, but in broad burning regions, each one feeding the next stage of the star's last life. The old image is an onion, and it remains useful. Not because the star is solid, and not because the layers are calm, but because the star has become nested. The surface hides almost everything. Beneath it, the star holds shells within shells, each one hotter than the one above. Near the center, the products of millions of years of fusion have gathered into a core that grows heavier by the hour. The star is no longer simply shining. It is assembling the conditions for its own collapse. The final fuel is silicon. In the last stage before disaster, silicon nuclei are transformed through a chain of reactions into iron group elements. This does not take millions of years. It does not take thousands. In a massive star near the end, silicon burning can run through its course in about a day. A star that spent ages as a point of light in a galaxy may complete its final, useful reaction during a single turn of a planet far away. Nothing on the surface needs to reveal this. The star may still shine across space, broad and luminous, while its center is quietly becoming unable to save itself. Iron is different. Up to this point, fusion has paid the star back. Hydrogen into helium gives energy. Helium into carbon gives energy. Carbon, neon, oxygen, and silicon can still take part in reactions that help support the core. Iron does not offer the same bargain. Around iron, the curve of nuclear binding reaches its peak. Iron nuclei are among the most tightly bound common nuclei in nature. To fuse iron into heavier elements does not release useful energy for the star. It takes energy away. That is the wall. The star has spent its life climbing toward heavier elements, and every earlier step has helped it hold back gravity for a little longer. Iron is the place where the staircase ends. The core can grow hotter, denser, and more massive. But iron fusion will not become a new engine. The star cannot light another long-burning fire in its center. It has reached a kind of silence inside the heat. The iron core is not cold. It is unimaginably hot by ordinary standards. It is packed with particles moving at high energy. It is surrounded by shells that may still be burning and dropping more iron group material onto the center. But the core is no longer producing the pressure it needs through fusion. It is supported by other effects, especially by the resistance of electrons forced into crowded quantum states. That support is real. For a time, it holds. The electrons in the iron core are fermions, particles that cannot all fall into the same quantum condition. As the core is squeezed, these electrons provide a kind of pressure, even when heat is not enough. This electron degeneracy pressure is one of the quiet rules of matter. It can hold up the remnants of smaller stars for longer than the universe has yet existed. In a white dwarf, the exposed core of a sun-like star, electron degeneracy pressure is enough. The object can cool for billions of years and remain intact. But the iron core inside a massive star is moving toward a limit. As silicon burning in the surrounding shell continues, more mass settles onto the center. The core grows. Its own gravity strengthens. The electrons are squeezed harder, driven into higher energies, until the support they provide approaches the point where it can no longer rise fast enough. There is a mass above which electron degeneracy pressure fails. It is known as the Chandrasekhar limit, and for an iron core, it lies near 1.4 times the mass of the Sun. The exact number depends on the composition and conditions, but the meaning is clear. Below the limit, the core can still resist. Above it, the old support gives way. The star has no new fuel waiting in the center. It has no deeper fire to ignite. Iron does not help. The electrons can no longer hold the weight. Gravity, which has been present from the first moment of the star's life, begins to take the core for itself. The change is swift compared with the long burning that came before. A core that took millions of years to build can lose its balance in less than a second. The scale is difficult to hold in the mind. Matter that once occupied a region, thousands of kilometers wide, begins to fall inward at a large fraction of the speed of light. The empty spaces inside atoms are removed. Electrons are pressed toward nuclei, the familiar architecture of matter, with electrons spread around compact centers, is no longer able to survive. Before that collapse begins fully, there is a strange stillness in the story. The star is enormous. Its outer layers continue to glow. Light still leaves the surface, carrying the appearance of a living star into space. Somewhere far away, an observer might see only a bright supergiant, a point of color in a telescope, a star among other stars. But deep inside, the center has crossed into another kind of physics. The outward supports that kept the star open have narrowed to almost nothing. The universe often hides its sharpest changes under surfaces that look unchanged. A calm sea can conceal a current below. A mountain can hold pressure along a fault for centuries. A massive star can shine while its core is already near failure. The surface does not know what the center has become. Light from the photosphere is slow to tell the truth. Gravity has no need to wait. Inside the core, density climbs. Electrons are forced closer to protons. The iron nuclei are exposed to temperatures and pressures that tear at their structure. Some high-energy photons break heavy nuclei apart in a process called photodisintegration, which consumes energy when the core can least afford to lose it. The collapse feeds on its own conditions. The hotter and denser the center becomes, the more support is removed. The matter falls inward more freely. This is the last moment before the neutron star has a name. It is not yet a neutron star. It is not yet a black hole. It is a collapsing stellar core in the narrow passage between forms of matter. Above it, the star still holds its layered body. Around it, the shells of older burning are being overtaken by a change that begins at the center and moves faster than sound can warn the outer layers. Beneath the old light, a new object is being prepared. The star has run out of the kind of fire that can save it. Its life has not ended because it became dark. It has ended because the center reached iron, and iron would not burn for support. The long contest between pressure and gravity has shifted. For millions of years, fusion answered gravity with light. Now the answer is gone. The core begins to fall, and in that falling, the ordinary matter of the star is about to be remade. For the outer star, the message has not yet arrived. The layers above the core are still falling and burning according to the old balance, unaware that the foundation beneath them has disappeared. The delay is brief, but it matters. It means the death of the star begins as a secret at the center, in a region no telescope can see directly. The first visible sign will come later, when the collapse sends its consequence outward. For now, there is only the inward motion, the tightening of matter, and the quiet crossing of a boundary that no star can cross twice. The collapse begins where no light from the surface can reach. It begins in the iron core, in matter so hot and crowded that the old rules of a living star no longer apply. For millions of years, gravity has been held in a long and careful balance by fusion. The balance has shifted from fuel to fuel, from hydrogen to helium, from helium to carbon, and onward through heavier elements. Now the center is iron-rich, and iron cannot give the star the pressure it needs. The core has become heavy enough for its own weight to outrun the electrons that once resisted it. The pause ends. At first, the motion is inward everywhere. There is no single crack, no visible wound, no ordinary explosion. The collapse is a change in the entire core at once, a falling of matter toward the center under gravity that has suddenly found open space in front of it. Atomic structure begins to fail. The wide emptiness inside atoms, the distance between electrons and nuclei, that makes ordinary matter feel spacious at the smallest scale, is squeezed away. What was once a sea of iron nuclei and electrons becomes a place where the separation between particles can no longer be preserved. A region comparable in size to a small planet contracts toward the scale of a city in less than the time between two heartbeats. This is not a slow settling. It is a plunge. Layers of matter fall inward so quickly that the outer parts of the core do not have time to adjust smoothly to what the inner parts are becoming. Signals in matter cannot travel infinitely fast. Pressure cannot reorganize the star instantly. Gravity acts, and the core obeys. As the density rises, electrons are driven into protons. In ordinary atoms, electrons occupy the space around nuclei, bound by electromagnetic force, but still separate from the protons inside. During core collapse, the pressure makes that arrangement impossible. Electrons and protons combine through a process called electron capture, producing neutrons and neutrinos. The star is not merely being compressed, its matter is being rewritten. This change is simple to describe and difficult to imagine. One electron and one proton become one neutron, while one neutrino slips away, repeated over a stellar core. The process transforms the character of the material. A core once built from nuclei surrounded by electrons moves toward a state dominated by neutrons. The electric charge that helped define ordinary atoms is reduced. The familiar distinction between nucleus and surrounding electron cloud begins to disappear. Matter is being pushed toward a form closer to the inside of an atomic nucleus, but on a scale that nature almost never permits. The neutrinos carry away energy. They are among the most elusive particles known, almost massless, without electric charge, able to pass through ordinary matter with extraordinary ease. A wall of lead many light years thick would still fail to stop all of them. Inside the collapsing star, they are produced in numbers beyond ordinary language. For a brief time, the core becomes one of the brightest neutrino sources in the universe. Most of the energy released by the collapse does not emerge as visible light. It leaves first as neutrinos, streaming outward through layers of star that are still falling inward. For most of the collapse, even the dense body of the star is almost transparent to them. They move through the matter that would stop photons, through plasma and nuclei, through the outer layers that have not yet learned the center has failed. Only in the deepest and densest region do some neutrinos become trapped for a moment, scattering again and again before escaping. The star is becoming so dense that even ghost-like particles begin to notice it. While neutrinos flee, the core continues to shrink. The density climbs toward nuclear density, the density found inside atomic nuclei. This is the point where individual neutrons can no longer be treated as distant particles in a broad, empty space. They are crowded so closely that the strong nuclear force and the quantum nature of fermions begin to dominate the motion. The collapse that looked unstoppable finds a new resistance, not from heat, not from fusion, and not from any material strength known on Earth, but from the behavior of matter, when almost all of its empty space has vanished. The inner core stiffens. It does not become solid in the ordinary sense. It becomes resistant in a deeper way. As the matter reaches nuclear density, the newly formed neutrons and the repulsive part of the nuclear force oppose further compression. The innermost region, which has been falling inward, slows sharply and rebounds. The word bounce can sound too gentle for what happens, but it is the right shape of the event. The inner core halts, overshoots, and pushes back against the material still rushing down from above. Above that rebounding center, the rest of the core is still falling inward at enormous speed. It has not stopped. It collides with the stiffened inner core and is forced to change direction. A shock wave forms at the boundary, a shell of compressed energy moving outward through matter that is still pouring inward. For a brief moment, the newborn neutron core sends an answer back into the star. The answer almost fails. The shock wave begins with immense energy, but the star around it is dense and heavy. As the shock travels outward, it spends energy breaking apart heavy nuclei. Iron group nuclei are split into protons and neutrons, and this photodisintegration drains the shock. At the same time, matter continues to fall onto it from above, pressing inward against its motion. The shock slows. It stalls. The star has begun to explode, and yet the explosion hesitates inside it. This hesitation is one of the most important moments in the death of a massive star. If the shock cannot be revived, the outer layers will continue to fall. The forming neutron star may gain too much mass. Gravity may take everything inward, and the result may be a black hole with little or no bright supernova. The difference between an explosion and a quiet collapse can depend on details hidden deep inside the star, where neutrinos, turbulence, rotation, magnetic fields, and the structure of the original star all matter. In many cases, the neutrinos help turn hesitation into release. Only a small fraction of the neutrino energy is absorbed by the material behind the stalled shock, but a small fraction of an enormous amount can still be enough. The neutrinos heat the region below the shock. They stir it. They raise pressure where the shock needs support. Slowly, unevenly, the stalled front can be revived. It begins to move outward again, not as a neat sphere, but as a disturbed, boiling surface of energy passing through the broken heart of the star. The explosion grows from the inside outward. The outer layers of the star are lifted and accelerated into space. Shells that once burned hydrogen, helium, carbon, oxygen, and silicon are torn away from the compact remnant at the center. The star opens. Matter that had been bound by gravity is thrown into the surrounding darkness at thousands of kilometers per second. For a time, the dying star can shine with the brightness of a whole galaxy, not because its center has found a new life, but because its death has released the stored energy of collapse. The light that eventually reaches the outside is late compared with the neutrinos. Photons must fight their way through expanding debris. They are absorbed and re-emitted, scattered and delayed, until the outer layers become transparent enough for the supernova to glow fully. To a distant observer, the star may suddenly brighten where a faint point once rested. The signal appears as light, but the deeper story began earlier, in particles that left the core almost immediately and crossed space with little interference. A supernova is not only destruction, it is also transport. The explosion carries elements into the interstellar medium, the thin gas and dust between stars. Some of those elements were made during the star's life, in the long sequence of fusion from hydrogen upward. Some were shaped in the shock itself. Some of the heaviest elements are made in other events as well, especially in neutron star mergers, where neutron-rich matter is thrown out and rapidly builds heavy nuclei. The full origin of every heavy atom is a wider story, but the supernova remains one of the great ways the universe returns stellar material to space. Carbon, oxygen, silicon, iron, and many other elements leave the dead star and drift outward. The debris does not keep the shape of the original star for long. It expands, cools, mixes, and becomes part of a larger cloud. Over long periods, that cloud may be stirred by other explosions, compressed by passing waves, and folded into regions where new stars form. The death of one massive star becomes part of the raw material for later systems. The boundary between an ending and a beginning is not sharp in a galaxy. Matter remembers through reuse. At the center of the expanding remnant, the newborn compact object remains. It is small compared with the star that made it, so small that the entire drama of collapse has left behind something that could fit within the width of a large city, yet it carries more mass than the sun. The remnant is hot beyond ordinary comparison. Its surface radiates X-rays. Its interior is still settling. Neutrinos continue to carry away heat. Around it, the debris of the supernova races outward, becoming a shell, a cloud, and eventually, a faint structure spread across light years. This central remnant is a neutron star, if its mass remains below the limit that gravity can overwhelm. In its first moments, it is not the cold, stable object that later observations may reveal. It is newborn, vibrating, cooling, and perhaps spinning rapidly. The collapse that formed it has preserved angular momentum, so the smaller object rotates much faster than the core that came before. Its magnetic field, compressed and intensified by the collapse, may thread space around it with tremendous strength. The dead star has become something compact, precise, and severe. The new neutron star is not made of normal atoms. Its outermost layers may still contain nuclei and electrons, but deeper inside, the material is mostly neutrons, crowded to densities near and above nuclear density. The phrase "mostly neutrons" can sound simple. The matter is layered, curved by gravity, heated by birth, and governed by quantum rules. But the broad transformation has already happened. Electron capture has removed much of the old atomic architecture. The collapse has made a star-sized remnant out of nuclear matter. For a short time, the surface is wrapped in the violence of its formation. Fallback material may rain back down. Some of the ejected matter, not moving fast enough to escape, can return and add mass to the remnant. This fallback matters. A neutron star born safely below its maximum mass may survive. One born close to the limit may be pushed over it by returning debris. In that case, the newborn neutron star may live only briefly before collapsing again, this time into a black hole. Some deaths have more than one stage. The supernova remnant around the star expands into the galaxy. Its shape depends on the structure of the surrounding gas, the asymmetries of the explosion, and the motion of the original star through space. The newborn neutron star may receive a kick during the explosion, a recoil caused by uneven ejection of matter or asymmetric neutrino emission. Some neutron stars are flung through space at hundreds of kilometers per second. They leave the birthplace of the supernova behind, moving like dark embers through the galaxy. Long after the supernova fades from view, the neutron star may continue alone. If its magnetic poles sweep beams of radiation across Earth, it may be seen as a pulsar. If its magnetic field is unusually powerful, it may behave as a magnetar. If it has a companion star, it may draw material from that companion and shine in X-rays. The object born from collapse can have many later faces, but the birth itself always points back to the same deep transition from a failing iron core to matter held at nuclear density. The collapse also changes the relation between the star and time. The massive star may have lived for millions of years. Its final silicon burning may have lasted about a day. The core collapse takes less than a second. The neutrino burst lasts only seconds. The bright supernova may glow for weeks or months. The neutron star that remains can persist for millions, billions, or longer. A brief inward fall creates one of the longest-lived compact structures in the universe. There is a stillness after the violence, but it is not emptiness. The remnant is hot, the crust is forming, the interior is cooling. The magnetic field is settling into a configuration that may later crack the crust or power beams of radiation. The supernova debris continues outward, thinning into the interstellar medium. Somewhere in that expanding cloud, atoms that once belonged to the star begin their slow departure from the place of collapse. They will not know the compact object left behind. They will become dust, gas, planets, or living chemistry in some later age. The neutron star remains at the center of the story because it is the part that did not escape. It is what gravity kept. The outer star is returned to space, bright and scattered. The core is compressed into an object that should seem impossible by everyday intuition. It is not supported by burning fuel. It is not held up by ordinary strength. It is not a planet, not a normal star, and not yet a black hole. It is the answer created when collapse goes almost all the way, then stops. The next question is the same one that rises from the remnant itself. How can anything stop there? How can matter with more mass than the sun remain as an object only kilometers across? The explosion explains how the neutron star is born, but not why it survives. To understand that, the story has to move closer to the remnant, into its density, its gravity, and the strange condition of a city made from the matter of atomic nuclei. After the supernova has opened the star and sent its outer layers into space, the center remains. It is not bright in the way the old star was bright. It does not fill a solar system with a swollen atmosphere. It does not burn through fuel, or hold itself open by fusion, or glow with the broad, familiar light of a living sun. It is small enough to hide inside the outline of a large city, and heavy enough to carry more mass than the sun. The old star has become a compact remnant, and the remnant is a neutron star. From far away, such an object can seem almost absent. It may be no larger than 20 or 30 kilometers across. On the scale of a galaxy, it is less than a grain. A telescope does not see a surface like the surface of a planet, with continents and oceans and clouds. It may see pulses of radio light, X-rays from hot regions, or the faint thermal glow of a young remnant cooling in space. The object itself is too small for ordinary sight at interstellar distance. Its presence is known by what it does to light, to magnetic fields, to nearby gas, and to the timing of signals that cross the dark. The smallness is part of the difficulty. A neutron star is not simply a dense star. It is what remains when a stellar core has been compressed to the point where matter has lost almost all the emptiness that once gave atoms their size. The body of the star may contain 1.4 solar masses, or sometimes closer to 2. That means more matter than the Sun, forced into a sphere whose diameter is less than the distance across many cities. The comparison is not exact because no city has edges like a neutron star has edges, and no city carries a gravitational field that changes the path of light. But the image gives the first shape of the truth. A sun has been folded into a place where streets could cross from one side to the other in less than an hour. Density is the first property that has to be approached slowly. Ordinary matter feels solid because atoms resist being pushed into the same space, but atoms are mostly empty volume. A nucleus sits at the center, small and heavy, while electrons occupy a wide region around it. If an atom were expanded until its nucleus had the size of a small bead, the electrons would lie far away, with almost all the atom between them made of empty room. In a neutron star, that room is gone. The core collapse has pressed electrons and protons together. The star is built from matter packed close to nuclear density. A small sample of such matter is not something that could rest on a table. A spoonful, if it could be removed and brought to Earth without expanding, would outweigh mountains. A cube the size of a sugar crystal would carry the mass of a landscape. The surface beneath it would not hold. Rock, metal, and diamond would offer no meaningful resistance. The sample would pass downward, not because it is sharp, but because its weight is concentrated into too little area for any ordinary material to bear. The Earth itself would be too soft a place for neutron star matter. These comparisons are only shadows of the real condition. A neutron star is not a container filled with heavy material. The whole object is the material. Its gravity is part of its structure. Its density, pressure, and curvature are tied together. The star holds its own matter in a form that cannot belong to gentler environments. At the surface, gravity is already far beyond anything found on ordinary worlds. On Earth, a dropped stone gains speed in a familiar way. Near a neutron star, a small object falling from only a short height would strike the surface at a large fraction of the speed of light. There is no soft arrival. The energy released by impact would be enormous, far beyond the chemical energy of any explosion. Matter landing on a neutron star does not land in the usual sense. It is flattened, heated, and absorbed into a crust that lies under one of the strongest gravitational fields that matter can endure without disappearing behind an event horizon. Escape is almost impossible. To leave Earth's surface, a spacecraft must reach a little more than 11 kilometers per second. To leave the surface of a neutron star, the required speed can be a substantial fraction of the speed of light. The exact value depends on the star's mass and radius, but the meaning is clear. Light itself struggles in the gravitational well. It can escape from outside the event horizon, but it loses energy as it climbs away. Radiation born at the surface reaches distant space, stretched to longer wavelengths, reddened by gravity. The star bends and drains its own light. The bending is not small. General relativity says that mass curves spacetime, and near a neutron star, the curvature is severe. Light that leaves one side of the star may curve around enough for a distant observer to see more than half the surface at once. The back is not completely hidden in the way the far side of a planet is hidden. Gravity tilts the rules of sight. The star shows part of itself around its own edge. This strange visibility will matter later when modern X-ray instruments use the shifting brightness of hotspots to infer the size of the star. Even the way light escapes becomes a clue to what lies beneath the crust. Close to the surface, tides become destructive. A tidal force is the difference in gravity from one end of an object to the other. On Earth, this difference raises ocean tides and stretches the planet slightly under the pull of the moon. Near a neutron star, the difference is not gentle. The side of an approaching object closer to the star is pulled much harder than the side farther away. The object is stretched along the direction of falling and squeezed sideways. Chemical bonds cannot survive that difference. Molecules are torn apart. Atoms are stripped. Matter becomes a thin stream before it reaches the surface. This process is often called spaghettification, though the word can sound almost playful. Around a neutron star, it is only a description of gravity's gradient. The star does not need to touch matter to destroy its shape. The field around it is enough. A planet passing too near would be torn, heated, and spread into debris. Gas from a companion star can be drawn into a disk, flattened by rotation, glowing as friction and magnetic fields turn gravitational energy into radiation. Around some neutron stars, this falling material shines in X-rays, making the compact object visible across great distances. The surface itself is not a surface in the ordinary planetary sense. There is no ocean wave, no soil, no loose stone. The outermost atmosphere may be only a thin layer, crushed flat by gravity. Beneath it, nuclei are arranged in a dense solid crust, possibly smoother than any solid surface on Earth at large scales, because gravity allows almost no height. A mountain on a neutron star cannot rise like a mountain on Earth. Any bump is pressed down by its own weight. Even a small irregularity may carry more mass than a terrestrial mountain range, but its height may be measured in fractions of ordinary distances rather than in peaks and ridges. The crust is also under strain. It is made of nuclear matter in a lattice, threaded by magnetic fields, and coupled to deeper layers that may move as superfluids. The star rotates. It cools. Its magnetic field evolves. Stress builds. When the crust shifts, the release can send energy outward as bursts of high-energy radiation. In magnetars, where magnetic fields are stronger than in ordinary neutron stars, these crustal fractures can be seen across the galaxy. A surface only kilometers wide can affect space around it on a scale that feels out of proportion until the stored energy of the magnetic field is considered. Rotation gives the neutron star another strange face. The original stellar core had angular momentum before it collapsed. When that core shrank from a region thousands of kilometers across to a remnant only a few tens of kilometers wide, the rotation rate rose sharply. The same principle appears in a skater pulling in her arms, but the scale is different enough to make the comparison almost fragile. A slow-turning stellar core can become a neutron star rotating many times each second. Some rotate hundreds of times each second. Their surfaces move at speeds that press against the limits set by gravity and the strength of the crust. If the magnetic axis does not align with the rotation axis, beams of radiation can sweep through space. The result is a pulsar. The star turns, and its beams pass across distant worlds like a lighthouse beam crossing dark water. The pulse does not mean the star is turning on and off. It means the beam points toward the observer once per rotation. The regularity can be startling. Some pulsars keep time with a steadiness that rivals carefully built clocks. Their signals arrive again and again, shaped by the rotation of an object made from matter at the edge of collapse. A pulsar is useful because it carries information. Its period reveals rotation. Changes in that period reveal the gradual loss of energy as the star slows. Tiny irregularities can hint at motion inside the star. In some pulsars, the rotation suddenly jumps by a small amount. These events are called glitches. They are thought to come from exchanges of angular momentum between the solid crust and a neutron superfluid deeper within. The surface clock stutters because matter under the crust has moved. A pulse arriving from thousands of light-years away can carry news from a state of matter that no laboratory can hold. The magnetic field is another extreme. A normal neutron star may have a magnetic field billions or trillions of times stronger than Earth's. A magnetar goes further. Its field can reshape atoms and store enough energy to produce intense bursts when the crust yields. In such a field, the ordinary picture of electrons around nuclei becomes distorted. Matter near a magnetar is forced into shapes dictated by magnetism as much as by bonds. Yet the neutron star does not fly apart under these energies. It does not continue inward under its own gravity either, as long as its mass remains below the final limit. This is the narrow condition that makes it so strange. The object is violent in its surroundings and stable in its structure. It can emit pulses, bursts, and X-rays. It can tear gas from a companion star. It can cool over long ages, and still keep its form. The stability is not the stability of stone. It is the stability of a balance deeper than heat. This balance can be felt in the numbers, but the image matters more. Picture a sphere smaller than a city, surrounded by the thinning debris of the star that made it. It turns in darkness. Its magnetic field reaches far beyond its crust. Light, leaving its surface, is bent and reddened. Time itself runs slightly differently near it than it does far away, because gravity changes the rate at which clocks tick. The star is not a black hole. Light can still escape. Structure still exists. There is still a crust, an atmosphere, a core, and a history. That distinction is delicate. A black hole has an event horizon, a boundary beyond which light cannot return. A neutron star has no such horizon. Its surface is real, even if no ordinary object could survive there. It can be struck by falling matter. It can radiate heat. It can crack. It can pulse. It can have magnetic poles and hotspots. The universe can still receive information from it. However severe the gravity becomes, the neutron star remains on the side of reality, where matter can be observed. This makes it one of the last forms matter can take before structure is lost. A white dwarf is dense, but its atoms, though compressed, still retain nuclei and electrons in a broader arrangement. A neutron star goes further. It is not supported by ordinary atomic structure. It is supported by the compressed quantum behavior of neutrons and by nuclear forces at distances so small they belong to the scale of nuclei. It is matter pushed nearly to the end of matter, but not past it. The silence around such an object is misleading. It may sit alone between stars, invisible to ordinary telescopes, cooled and dimmed after millions of years. It may no longer pulse toward Earth. It may not feed from a companion. It may have no bright nebula around it. Still, inside, the balance remains. Gravity presses inward with almost unimaginable strength. Quantum pressure and nuclear forces answer from within. The star holds. It does not need fuel to do this. It does not need to shine brightly. It is held up by the nature of the particles from which it is made. That is why the question becomes sharper after the star is seen in its physical form. A supernova can explain the birth. It can explain the heat, the debris, the sudden compactness, and the first burst of neutrinos. It cannot by itself explain the long survival. A city made of neutrons should seem, by ordinary instinct, like a temporary thing. Gravity appears too strong. The mass appears too great. The radius appears too small. The next inward step seems inevitable. But ordinary instinct was built for weak gravity and low density. It was built for rocks, air, water, and bodies made from atoms with space inside them. A neutron star belongs to a different regime. The answer to its survival does not come from the surface, or from its heat, or from any material strength. It comes from a rule that operates below atoms, a rule that determines why matter occupies space at all. The star remains because its neutrons are not free to become identical in every way. The collapse has reached the place where quantum mechanics begins to push back. The answer begins far below the surface, below the crust, below the visible glow, below even the idea of atoms as ordinary matter understands them. A neutron star survives because the particles inside it obey a rule that has no weight, no temperature, and no fuel. It is not a wall in space. It is not a spring hidden in the core. It is not a pressure made by heat, like gas pressing against the inside of a balloon. It is a law about identity. Certain particles cannot be made exactly the same. The star is still under gravity. That never changes. Every piece of its matter pulls on every other piece. The surface presses down on the crust. The crust presses down on the inner layers. The inner layers press down on the core. If gravity alone were allowed to finish the work, the whole object would continue inward, past every familiar density, past every ordinary state of matter, until the remnant crossed the boundary of a black hole. Yet the neutron star stops before that boundary as long as its mass remains low enough. Something inside it answers the inward pull. The first clue comes from a simple fact about particles. Matter is not made from one kind of thing. The particles that build atoms belong to a family called fermions. Electrons are fermions. Protons are fermions. Neutrons are fermions. These are the particles that make solid matter, liquid matter, gas, stars, dust, planets, bones, stone, and metal. They are not free to behave like light. They do not pile into one state without limit. They carry a hidden discipline in the way quantum mechanics describes them. The rule is known as the Pauli exclusion principle. It says that two identical fermions cannot occupy the same quantum state at the same time. The words sound technical, but the shape of the idea is plain enough. For identical fermions, nature does not allow perfect sameness. If one neutron has a certain set of properties inside the star, another neutron of the same kind cannot take exactly the same full condition. It must differ in some quantum way. It must occupy another state. This is not a force in the usual sense. It is not like magnetism, where one pole pushes another. It is not like pressure from hot gas, where moving particles strike a wall. The forbidden arrangement simply has no allowed description. In the mathematics of quantum mechanics, the probability of two identical fermions occupying the same state is zero. Not small, not unlikely, zero. The universe leaves no path for that configuration. That refusal shapes everything ordinary matter becomes. In an atom, electrons cannot all sink into the lowest possible state around the nucleus. The first available states fill, then higher states must be used. Because of this, atoms have shells. Because atoms have shells, elements behave differently. Carbon does not act like oxygen, sodium does not act like neon, iron does not act like hydrogen. Chemistry begins with this refusal. The difference between a gas and a metal, between a crystal and a living cell, reaches back to the fact that fermions cannot all become one another. Solidity also begins there. When a hand rests on a table, the atoms do not actually touch in the old mechanical picture of hard balls meeting hard balls. The electron clouds of the atoms resist being pushed into the same states. Electromagnetic forces matter too. But beneath the familiar feeling of contact lies this quantum ordering. Matter keeps its volume because its fermions cannot be compressed into complete sameness. The table feels solid because the particles in it and the particles in the hand are not allowed to collapse into the same set of states. In most places, this rule works quietly. It is hidden under the ordinary behavior of materials. Heat, chemical bonds, crystal structures, and electromagnetic forces make the world feel understandable. The Pauli principle sits beneath them, rarely noticed. In a neutron star, the covering layers are stripped away. The rule becomes one of the main pillars holding up an object heavier than the sun. To see how the pressure appears, imagine a large number of identical fermions placed into a shrinking volume. The particles fill the lowest available quantum states first. That is the calmest arrangement. But because no two identical fermions can share exactly the same state, the lower states fill up. As more particles are added, or as the available space becomes smaller, later particles must occupy states with higher momentum and higher energy. The crowding does not make them hotter in the ordinary sense. It forces them into motion-like states required by quantum mechanics. This is degeneracy pressure. It is pressure created by the filling of quantum states. The name can sound cold and abstract, but inside a compact star, it becomes a real support against gravity. The particles at the top of the filled sequence carry high momentum. High momentum means they resist further confinement. They press outward. Gravity tries to reduce the volume. Quantum mechanics raises the energy cost of doing so. A balance becomes possible. The strange part is that this pressure does not require heat. A classical gas loses pressure as it cools, because its molecules move more slowly. At absolute zero, in the old classical picture, the motion would stop and the pressure would vanish. A degenerate gas of fermions does not behave that way. Even at the lowest temperature allowed by physics, the particles cannot all fall into the same lowest state. They still fill a ladder of quantum states. The upper rungs remain occupied. The pressure remains. That is why a compact remnant can survive after its fire is gone. A normal star needs fusion in its core to hold back gravity. When fusion changes, the star changes. When fusion ends, the star must find another form of support or collapse. A white dwarf has already shown one version of this answer. It is the remnant of a smaller star, a body roughly Earth-sized but with a mass similar to the Sun. It no longer fuses elements in its core. It shines only because it is still hot from its earlier life. Over long ages, it cools. Yet it does not collapse simply because it cools. A white dwarf is held up by electron degeneracy pressure. Its electrons are compressed into a dense sea, forced by the Pauli principle to occupy many different states. The pressure from those electrons is enough to balance gravity for a star remnant below the Chandrasekhar limit. It does not need new energy. It does not need a burning center. It can fade and still remain a star-sized ember made stable by quantum mechanics. But electrons are light particles. As a white dwarf becomes more massive, gravity squeezes them harder. They occupy higher and higher momentum states. Eventually, many electrons move so close to the speed of light that the relationship between compression and pressure changes. The pressure still grows, but not fast enough. At the Chandrasekhar limit, electron degeneracy pressure can no longer support the mass. The white dwarf cannot remain a white dwarf above that threshold. For the iron core of a massive star, reaching this kind of limit begins the collapse. During that collapse, electrons are driven into protons, and the matter becomes rich in neutrons. The support that failed was made by electrons. The new support, if the remnant is to survive, has to come from neutrons. Neutrons are also fermions. They obey the same Pauli exclusion principle. They too cannot all occupy the same quantum state. When compressed to nuclear density, they generate their own degeneracy pressure. The difference is mass. A neutron is much heavier than an electron. Because of that, neutron degeneracy becomes important at far higher densities. Electrons reach the limits of their support, while matter is still much less dense than a neutron star. Neutrons can be packed more tightly before their quantum pressure enters the most severe regime. This is one reason the collapse can pass beyond a white dwarf state and still stop before a black hole. Electron pressure fails. Neutron pressure takes over. Inside the neutron star, the particles are no longer arranged as ordinary atoms. In the deeper regions, there is not enough room for that. Neutrons dominate the matter, crowded together near the density of atomic nuclei. The Pauli principle forces those neutrons into a filled sea of quantum states. More compression means forcing them into even higher energy states, and that produces resistance. Gravity presses inward. The neutron sea presses outward. There is also the nuclear force. At the distances inside atomic nuclei, protons and neutrons feel the strong nuclear interaction. Over certain ranges, this force is attractive and binds nuclei together. At very short distances, it becomes strongly repulsive. It does not let the particles overlap without cost. In the dense interior of a neutron star, where neutrons are packed close together, this repulsive part of the nuclear force adds to the support. The star is held by both the filling of quantum states and the short-range behavior of nuclear matter. The two forms of support are intertwined. Near some densities, the Pauli principle supplies much of the resistance. Deeper inside, nuclear interactions become increasingly important. The exact balance is not fully known because matter at several times nuclear density cannot be recreated and held in laboratories on Earth. Particle accelerators can create very hot matter for very brief moments, but a neutron star holds cold, ultra-dense matter under gravity for astronomical time. The relationship between pressure and density in this hidden matter is called the equation of state. It is one of the central unsolved maps in neutron star physics. A stiff equation of state means matter resists compression strongly, producing larger stars for a given mass and allowing heavier neutron stars before collapse. A soft equation of state means matter compresses more easily, making smaller stars and lowering the maximum mass. every measured neutron star mass, every radius estimate, every pulse of X-ray light, and every gravitational wave from a merger helps narrow the possibilities. For the sleeping remnant itself, the equation of state is not a formula written somewhere inside it. It is the way its matter responds to gravity. It decides how thick the crust may be, how large the radius can remain, how much the core can compress, and how close the star stands to the edge of collapse. The neutron star is a balance written as an object. Its radius is not arbitrary. Its mass is not arbitrary. Both are expressions of matter answering gravity under rules that belong partly to quantum mechanics and partly to nuclear physics. This makes a neutron star different from an ordinary hot object. A coal fades when it loses heat. A planet cools and changes its surface. A normal star dies when fusion can no longer provide pressure. A neutron star cools, but cooling does not remove the main support. Its inner temperature can fall over millions of years. Its surface can become dim. Neutrinos can carry energy away from the core. Photons can leave from the surface. The star may become harder to see. But the quantum pressure remains because the neutrons still cannot share states. There is a quiet severity in that. The neutron star does not survive because it is energetic, though it may be born hot. It does not survive because it is young, though young ones shine strongly. It survives because the rules of matter do not loosen with age. The Pauli exclusion principle does not tire. The strong nuclear force does not forget its short-range repulsion. Gravity pulls continuously, but the answer from the particles is continuous as well. At the same time, this support is not infinite. It can hold only so much mass. Adding matter makes the star more compact. Greater compactness increases central density. Higher density changes the pressure, the nuclear interactions, and the curvature of spacetime. If enough mass is added, the star moves toward the final boundary, where even neutron degeneracy pressure and nuclear repulsion cannot find a stable balance. The quantum refusal is powerful, but it is not absolute against all gravity. For now, below that boundary, the neutron star remains. Its existence is a meeting place between the smallest and largest descriptions of nature. A rule discovered to explain the arrangement of electrons in atoms becomes responsible for supporting a dead stellar core. A principle that shapes the periodic table also helps hold a city-sized star against collapse. The same refusal that gives matter its structure in quiet rooms and cold stones is acting inside a remnant born from a supernova. There is no need to imagine the particles choosing this resistance. They do not choose. A neutron does not decide to keep its state separate from another neutron. The separation is built into what a neutron is. Identity itself has a structure in quantum mechanics, and that structure prevents a certain kind of collapse. In the deep interior of the star, this abstract rule becomes weight-bearing. It becomes the difference between a surface and an event horizon. The neutron star is therefore not an object held up by strength in the ordinary sense. Strength belongs to materials that can crack, bend, or melt. The support here lies under material strength. It is not steel multiplied many times. It is not diamond made denser. It is a state where ordinary comparisons have ended, and the last supports come from quantum states and nuclear forces. Matter has been taken almost as far as it can go while still remaining matter. This is why the remnant after a supernova can wait in darkness for ages. The explosion is over. The outer layers are gone. The heat is leaving. The light grows weaker. Yet inside, the filled sea of neutrons continues to press back. Gravity and quantum mechanics hold one another in a narrow, long-lasting balance. The object is small, but the balance is vast. The next layer of the story lies within that balance itself. A neutron star is not a uniform ball, not a simple sphere of identical material from surface to center. It has an atmosphere crushed almost flat, a crust of exotic nuclei, a region where neutrons drip free, deeper layers that may flow without friction, and a core where matter may change into forms that have never existed on Earth. The rule that keeps the star from collapsing gives it stability, but the structure it supports is stranger than a single answer can contain. The inside of a neutron star cannot be entered, touched, drilled, or opened. It has no tunnel, no exposed cross-section, no sample that can be placed under a microscope and kept in its native state. Everything known about its layers comes from signals that leave the surface, from pulses that arrive with exact timing, from cooling curves, from bursts, from gravitational waves, and from the difficult mathematics of matter under pressure. The object is small enough to fit inside a city, yet its interior contains a sequence of worlds more alien than any landscape made of rock or ice. At the very outside is an atmosphere so thin that the word atmosphere almost feels too generous. On a normal planet, an atmosphere can rise for many kilometers before fading into space. Around a neutron star, gravity presses gas into a layer that may be only centimeters or meters thick. Even there, the density can be heavy by earthly standards. The atoms are stripped, ionized, and arranged by heat, gravity, and magnetic fields. Hydrogen may lie there, if the star has gathered it from a companion or from fallback material. Helium or heavier elements may dominate in other cases. The composition matters because this shallow layer is where much of the observable light begins its escape. Radiation leaving the atmosphere carries marks from the surface below. Its spectrum can reveal temperature. Its brightness can change as the star turns. Its path is bent by gravity before it travels outward into space. From far away, astronomers do not see this atmosphere as a place. They see a pattern in X-rays, a thermal glow, or a pulse. A layer thinner than a room can help measure an object heavier than the sun. Beneath the atmosphere lies the outer crust. Here matter begins to have something like solidity, though not solidity in the ordinary sense of stone or metal. Atomic nuclei are arranged in a crystalline lattice, held in place by pressure and by the sea of electrons moving among them. The nuclei near the surface may be iron group elements, the ashes of nuclear burning and collapse. They are packed far more closely than atoms in any terrestrial solid. The electrons are no longer bound to individual atoms in the familiar way. They move through the crust, carrying heat and electricity through matter, under a gravity that flattens every irregularity. The crust is thin compared with the whole star, perhaps about a kilometer or less depending on the mass and the equation of state. Yet this narrow shell can hold strain. It can crack. It can store magnetic stress. It can move slightly against deeper layers. In a magnetar, the magnetic field may twist the crust until it yields, releasing bursts of X-rays and gamma rays. The surface of the star, quiet from a distance, may be crossed by stresses no material on Earth could survive for even an instant. Descending through the outer crust, the pressure rises. Nuclei are pushed into states that would not survive outside the star. Electrons are squeezed closer to protons, and some are captured, changing protons into neutrons. The nuclei become more neutron-rich with depth. They grow heavier, swollen with neutrons, lying inside the electron sea like dense islands in a tightening ocean. The deeper the layer, the less familiar the word atom becomes. At a certain density, the nuclei reach a limit. They have taken in so many neutrons that they cannot hold them all. Extra neutrons begin to leak out. This boundary is called the neutron drip line. It is one of the quiet thresholds inside the star, less famous than the event horizon of a black hole, but just as clear in its own regime. Above it, neutrons are mostly bound inside nuclei. Below it, free neutrons begin to fill the spaces between them. The inner crust begins below that line. It is not a place of ordinary nuclei arranged in ordinary matter. It is a mixed state. Neutron, rich nuclear clusters, free neutrons, and electrons, all held under pressure that has no counterpart on Earth. The free neutrons are not simply drifting like a gas in a room. At low enough temperature relative to their density, they pair and form a superfluid. This means they can move without ordinary viscosity, without friction in the classical sense. A current in such a fluid can persist with strange patience. The word fluid can mislead. This is not water, not oil, not anything that pours in a cup. It is nuclear matter, behaving collectively under quantum rules. The neutrons form paired states, and those pairs act in some ways like bosons, able to share a common quantum condition. The result is a flow that does not lose energy by the usual channels. In the inner crust of a neutron star, a part of the star may be moving in a state that has no direct human-scale equivalent. Rotation makes this hidden flow visible indirectly. A neutron star spins, and over time many pulsars slow down as they lose energy through radiation and magnetic braking. The crust is tied to the magnetic field and follows this gradual slowing. The superfluid inside may not slow in exactly the same way. It stores angular momentum in quantized vortices, tiny rotating structures required by the mathematics of superfluid rotation. These vortices can become pinned to the crustal lattice. As the outer crust slows, tension builds between the crust and the superfluid. Then, sometimes, the vortices unpin. Angular momentum is transferred suddenly to the crust. The pulsar spins a little faster. From Earth, the change appears as a glitch, a sudden jump in the timing of pulses. It may be tiny, but it is measurable. A clock in the sky skips because a hidden superfluid has shifted inside a dead star. In that small timing change, the interior speaks. Deeper still, the nuclear clusters of the crust may lose their clean shapes. At densities near the bottom of the crust, theory suggests matter may arrange itself into strange geometries, sometimes called nuclear pasta. The name is informal, but the structures it describes are serious. Nuclei may stretch into rods, sheets, tubes, and folded phases because the strong nuclear force and electric repulsion compete under compression. Spherical clusters are no longer always the lowest energy form. Matter chooses shapes that sound almost soft, yet may create some of the strongest material in the universe. This nuclear pasta layer, if it exists as models suggest, may affect how the crust breaks, how heat travels, how the star vibrates, and how the crust couples to deeper superfluid matter. It may be thin, hidden, and unreachable, but it could influence signals that cross space. A name borrowed from a kitchen marks a state of matter made by pressure beyond imagination. Below the crust, the star enters the outer core. The lattice dissolves. There are no longer separate nuclei in the usual sense. Matter becomes a dense fluid made mostly of neutrons, with a smaller population of protons, electrons, and possibly muons, heavier cousins of electrons that can appear when the energies are high enough. The proportions depend on density and on the equation of state. The star is now in the region that holds most of its mass. The neutrons in the outer core are expected to be superfluid. The protons, though fewer, may pair as well and become superconducting. A superconductor carries electric current without resistance. In a neutron star, superconducting protons can help sustain magnetic structures over immense spans of time. Electrical currents that would decay in ordinary matter may persist because the medium does not resist them in the usual way. The magnetic field threaded through the star is therefore not a simple surface feature. It is tied to deep, cold, quantum matter. The outer core is also where cooling processes become important. Young neutron stars lose heat mainly through neutrino emission from their interiors. The exact rate depends on what particles are present and which reactions are allowed. Some cooling paths are slow, others are faster, if the composition and density permit them. By observing how neutron stars cool over time, astronomers test the hidden composition of the core. A fading surface can carry a clue from depths that never emit light directly. At the center lies the inner core. If the star is massive enough to have one, this is where certainty thins. The density may rise to several times the density of an atomic nucleus. The pressures are so high that neutrons themselves may no longer remain clearly separate. No laboratory can hold matter in this condition. Experiments on Earth can collide nuclei at high energies, and for brief moments they can produce hot, dense states. But the inner core of a neutron star is different. It is cold by nuclear standards, extremely dense, and held there by gravity for ages. Several possibilities remain open. One is that the core contains only neutrons, protons, electrons, and muons, interacting in ways that grow increasingly repulsive at short distances. Another is that new particles appear. Hyperons, which are relatives of protons and neutrons containing strange quarks, may become favorable at high density. Their appearance would change the pressure. It could make matter more compressible. That creates a problem, because some observed neutron stars are heavy enough that the inner matter must be able to support them. The question of how hyperons can appear without making the star collapse too easily is one of the puzzles of dense matter. Another possibility is that neutrons dissolve into their constituent quarks. A neutron is made of quarks bound by gluons. At high enough density, the boundaries between individual neutrons may blur, and quark matter may form in the center. This would not look like the hot quark-gluon plasma produced briefly in high-energy collisions. It would be a cold, dense phase, possibly containing up, down, and strange quarks. If strange quarks become part of the mixture, the core may contain strange quark matter. Some models even allow the idea of strange stars, compact objects made largely of this phase, rather than ordinary neutron-rich matter. None of these possibilities can yet be chosen with final confidence. The star keeps its deepest answer hidden. Observations can narrow the range. Heavy pulsars prove that the equation of state cannot be too soft. Radius measurements test how compact the star can be. Gravitational waves from mergers show how easily neutron stars deform under each other's tides. Cooling behavior tests which particles and reactions may exist inside. Each clue removes some possibilities and leaves others standing. The inner core is therefore not an empty mystery. It is a constrained mystery. The unknown is surrounded by evidence. It cannot be anything at all. It must produce enough pressure to hold observed masses. It must allow radii consistent with X-ray timing and gravitational wave data. It must agree with nuclear experiments at lower densities. It must fit the cooling of real stars. The hidden matter has room to surprise, but not unlimited room. A neutron star, seen this way, is not one object but a stack of physical regimes. A thin atmosphere, a dense outer crust, a neutron-rich inner crust, possible nuclear pasta, a superfluid and superconducting core, perhaps an inner region of exotic particles or quark matter. Each layer is tied to the others by pressure and gravity. The surface cannot be understood without the core. The pulse cannot be understood without the crust. The cooling cannot be understood without the particles that move unseen in the depths. The layers also change with mass. A lighter neutron star may have a lower central density and no exotic core at all. A heavier one may press its center into phases that a lighter star never reaches. Two neutron stars with similar radii may hide different interiors depending on their masses and histories. A star that has accreted matter from a companion may have a different crust from one born alone and left untouched. There is no single perfect interior drawn for all neutron stars. There is a family of answers. Still, some features remain. The star is bound by gravity so strongly that every layer is compressed beyond familiar states. It is supported by quantum pressure and nuclear interactions. Its matter is organized by the Pauli exclusion principle, the strong force, superconductivity, superfluidity, and relativity. It is not a simple ball of neutrons, even though the name suggests one. The name is useful, but the reality is layered and restless. This layered structure is why neutron stars matter so much to physics. They are not only remnants, they are laboratories, built by gravity and left in space. They test how matter behaves when pushed beyond the density of nuclei. They test how magnetic fields live inside superconducting matter. They test how superfluids rotate under a crust. They test how gravity curves light just above a surface. No machine on Earth can reproduce the whole object. The universe has made the experiment already. From the outside, the star may be only a pulse, a dot, or a source of X-rays. Inside, It is a deep arrangement of matter at the edge of what is known. Every layer carries part of the answer to why the star survives. The crust shows that matter can still form structure under enormous pressure. The superfluid shows that quantum behavior can fill a stellar interior. The core shows where current knowledge begins to fade. The whole object is stable, but not simple. Above it, space may be almost empty. Around it, old supernova gas may drift in faint arcs. The star turns in the dark, small enough to disappear between the points of ordinary starlight. Yet below its surface, the laws of matter are layered like a quiet map. The next step is to ask how such a map can be read from far away, when no probe can descend and no surface can be resolved. The answer comes through light that bends, pulses that change shape, and instruments that measure the rhythm of X-rays from a star too small to see. The next way into a neutron star does not go through its crust. It begins far above Earth, on the outside of the International Space Station, where an instrument watches the X-ray sky with patient timing. The instrument is called NICER, the Neutron Star Interior Composition Explorer. Its work is not to take a picture of a neutron star in the ordinary sense. No telescope can resolve such a tiny surface across hundreds or thousands of light years. Its work is quieter. It measures the arrival of individual X-ray photons, one after another, and lets time become a kind of microscope. This is a different kind of seeing. A neutron star is too small for its disk to appear as a disk. Its surface cannot be separated into visible continents of heat and shadow. But many pulsars have hot regions on their surfaces, places where charged particles follow magnetic field lines and strike the crust near the magnetic poles. These hot spots glow in X-rays. As the star rotates, the hot regions turn into and out of view, making the X-ray brightness rise and fall in a repeated pattern. The star is not merely shining, it is marking time. In that pattern, there is information. A larger neutron star bends light less strongly than a smaller, more compact one of the same mass. A more massive star bends light more strongly than a lighter one of the same radius. The shape of each pulse, the way it rises, softens, peaks, and fades, is shaped by gravity, rotation, surface temperature, spot geometry, and the path that light takes as it escapes. A pulse profile is not just a flicker. It is a distorted map of a surface that cannot be imaged directly. This is where general relativity enters the observing room. Light near a neutron star does not travel in straight lines in the simple Euclidean sense. The star's mass curves space-time, and light follows that curvature. A photon leaving the surface at an angle that would normally carry it away from the observer may bend into view. Parts of the far side of the star can contribute to the signal. The edge is not a clean hiding place. Gravity folds sight around it. The effect is strong enough that a distant observer can receive light from more than half the surface at once. This changes the pulse. If a hot spot rotates behind an ordinary round object, it would disappear sharply when carried beyond the limb. Around a neutron star, the hot spot fades more gently because some of its light can curve around the star and still escape. The degree of this bending depends on compactness, the ratio of mass to radius. That ratio is one of the keys to the star's interior. A soft object and a stiff object can have the same mass but different radii. In neutron star physics, soft and stiff do not mean texture under a hand. They describe how dense matter responds to pressure. If the matter is soft, gravity compresses it more easily, and the star becomes smaller. If the matter is stiff, pressure rises strongly against compression, and the star remains larger. Measuring the radius is therefore not a matter of geometry alone. It is a way of asking what the core is made of. The method is delicate. The X-ray photons arriving at NICER have crossed space, passed through the curved gravitational field of the neutron star, and reached detectors in Earth orbit. Each photon has an energy and an arrival time. By collecting many of them over many rotations, scientists build the pulse shape. They compare that shape with models of how hot spots would appear on neutron stars of different masses, radii, orientations, surface temperatures, and spin rates. The answer is not one simple number drawn from the sky. It is a range, narrowed by statistics and by physics. One of the first pulsars studied this way was PSR J30 plus 0451, a nearby millisecond pulsar. It spins hundreds of times each second, old and recycled, likely accelerated by matter taken from a companion in the past. Neisser found that its hot regions were not arranged in the simple way many diagrams had suggested. Instead of two neat spots placed opposite each other like the poles of a bar magnet, the emitting regions appeared to be in the same rotational hemisphere, with one shaped more like an arc. The star did not match the simplest picture. It was still orderly, but not simple. That matters because a pulse profile carries both the star's size and the map of its surface emission. A wrong assumption about the hotspots can lead to a wrong radius. The surface pattern has to be inferred together with the mass and radius, not pasted on beforehand. A neutron star does not owe its magnetic field to classroom symmetry. Its field may be offset, tangled, or shaped by the long history of crust, superconducting core, and magnetospheric currents. The pulse is a message from that complicated surface. Another crucial target is PSRJ 740 plus 6,620, one of the heaviest neutron stars measured with high confidence. It has a mass a little above 2 solar masses. That alone makes it a test. Any equation of state that cannot support such a heavy neutron star is not describing nature correctly. When Neisser and X-ray observations were used to estimate its radius, the result pointed to a star that is not dramatically smaller than lighter neutron stars. Dense matter, at least over some range, appears less easily squeezed than some models once allowed. This is a quiet but powerful result. A heavy neutron star with a radius still around the same broad scale as a lighter one suggests that the pressure inside rises strongly with density. The core does not simply give way. It resists compression. That resistance may come from nuclear interactions, from the way neutrons and protons behave at high density, and perhaps from whatever new forms of matter appear deeper in. The measurement does not open the star, but it narrows the room in which the answer can hide. The same kind of work has continued with other pulsars. Each one offers a slightly different angle on dense matter. A pulsar with a known mass from radio timing becomes a stronger target because part of the problem is already fixed. A nearby bright pulsar gives more photons. A rapidly spinning pulsar tests how rotation changes the surface and pulse shape. No single object provides the entire equation of state. A family of measurements begins to trace it. There is something calm about this method. It does not wait for catastrophe. It does not require two stars to collide. It uses ordinary rotation, repeated thousands and millions of times. A hot region turns across the line of sight. X-rays arrive. The pattern repeats. From those pulses, a model slowly learns how strongly the star bends light, and therefore how much mass is packed into how much space. The interior is read through rhythm. The idea can be held as an image. A small star turns in darkness. Its surface carries one or two warm patches, not wide oceans of light, but small regions heated by particles guided along magnetic fields. As each patch comes around, its glow rises. As it turns away, gravity keeps a little of it visible longer than ordinary sight would expect. The pulse softens at the edges. The star reveals its compactness by refusing to hide its far side completely. The X-rays that reach Neisser are faint, but they are counted carefully. Space around Earth is not perfectly quiet. There is background radiation, instrumental noise, stray light, and other sources in the sky. The analysis must subtract what does not belong to the pulsar and preserve what does. It must account for the instrument, the orbit, the energy of the photons, and the timing. The final result is built from many small acts of patience. This patience is necessary because radius is one of the hardest quantities to measure for a neutron star. Mass can sometimes be measured through orbital motion, especially when the neutron star has a companion. Radius is harder. The star is too small and far away for direct imaging. Yet radius is exactly what dense matter physics needs. A mass without a radius gives only part of the answer. Together, mass and radius place the star on a curve. That curve is where the equation of state leaves its trace. The equation of state is sometimes described as pressure versus density. In the star, it is more than a graph. It decides how the crust sits on the core, how deep the central density becomes, whether exotic particles can appear, and how close the star is to its maximum mass. A measured radius says whether the matter is allowing gravity to squeeze it tightly or whether it is pushing back harder. Each radius estimate is a small window into a place where nuclei have dissolved and ordinary material language fails. Light bending also reminds us that the outside of a neutron star is already relativistic. The method would not work the same way around a normal star. The sun bends light too, and that bending was one of the early tests of general relativity. But the sun's curvature is gentle compared with a neutron star's. Around a neutron star, the bending is part of every pulse. It shapes what can be seen. It turns gravity from an obstacle into a measuring tool. The star does not give up its interior willingly. It gives only indirect signs: a pulse shape, a cooling curve, a burst, a glitch, a gravitational wave. Modern neutron star physics is built from these remote clues. Each one comes from a different layer or different event. X-ray pulse modeling comes from the surface and the spacetime just above it. Glitches come from rotation and superfluid motion below the crust. Cooling comes from particles and reactions in the core. Gravitational waves come from deformation during the final moments of a binary in-spiral. The whole object is assembled in the mind from signals that never show the interior directly. That indirectness is not a weakness. It is the way astronomy has always worked. No one has held a star. No one has walked through a nebula. Matter in the sky is known through light, motion, spectra, timing, and gravity. Neutron stars simply make the method more severe. The object is small. The physics is extreme. The clues are subtle, yet the signals are real, and they arrive with enough structure to teach. There is also an unexpected link between the pulse and the unseen core. A hot spot on the surface is not made of core matter, but the way its light bends depends on the mass and radius of the whole star. The radius depends on how the deep interior supports itself. So a photon, leaving a shallow layer of hot atmosphere, carries, in its path, the influence of matter kilometers below. A surface glow becomes a messenger from the core. This is why the measurements matter beyond the individual pulsars. If neutron stars of different masses all show radii clustered in a narrow range, that points towards certain equations of state. If future measurements find a sharp change, with heavier stars becoming much smaller, that could suggest a phase transition in the core, perhaps to a softer form of matter. If very heavy stars remain large, the dense matter must be stiff enough to resist compression even deep inside. The pulse shapes do not answer every question, but they decide which questions remain possible. The work is still unfinished. Systematic uncertainties remain. Hotspot geometry can be complex. The atmosphere model matters. The background has to be understood. Independent teams can analyze similar data and obtain compatible but not identical radius ranges. This is how the map is drawn. Slowly, with overlapping measurements, with disagreement narrowed by better data rather than erased by assumption. The honest answer is not a single final radius for all neutron stars. It is a tightening set of constraints. That tightening has already changed the field. Some very soft models of dense matter are disfavored by heavy neutron stars and radius measurements. Some extremely stiff models are limited by gravitational wave data because very large neutron stars would deform too strongly during mergers. The surviving equations of state lie between those pressures, neither too soft nor too stiff, able to support heavy pulsars while still matching the way merging stars shake spacetime. Matter at nuclear density is being bracketed from above, below, and far away. NICER is one part of that bracketing. It watches not the grand collision, but the steady pulse. Its measurements belong to a quieter astronomy of repetition. A neutron star turns. Photons arrive. A hot spot comes into view, then curves away, then returns. The same motion repeats night after night in orbit around Earth. From that repeated motion, scientists infer the size of one of the densest objects that can still have a surface. The image is worth leaving intact. A city-sized star, too small to resolve, bends its own light so strongly that its hidden side is never entirely hidden. Its X-rays are counted by an instrument moving above Earth. Each photon carries a timestamp. Each timestamp becomes part of a curve. Each curve presses against a theory of matter. Somewhere in the depths of the star, neutrons, protons, and perhaps stranger particles produce the pressure that keeps the object from collapse. Far away, the shape of a pulse reveals that pressure by the way light escapes. The next clue comes from a less quiet event. Some neutron stars do not remain alone, turning for ages in the dark. Some are born in pairs. Over millions or billions of years, gravitational radiation draws them together. They spiral inward, deform one another, and finally merge. In those last moments, the stars themselves become instruments. Their tides write the stiffness of dense matter into ripples of space-time, and those ripples travel outward long after the surfaces have vanished into fire. There is a final boundary for a neutron star, and it is not drawn on its surface. Nothing visible appears there as a line. There is no bright ring around the mass that says matter may go this far and no farther. The boundary is hidden in the balance between pressure and gravity, in the way dense matter answers compression, and in the way general relativity changes the meaning of support. Below that boundary, a neutron star can exist for ages. Above it, the same matter has no stable place to stand. The boundary is called the Tolman-Oppenheimer-Volkoff limit. It is often shortened to the TOV limit, but the full name carries the history of the problem. Richard Tolman, J. Robert Oppenheimer, and George Volkoff worked with Einstein's theory of gravity to ask how much mass a cold, non-rotating neutron star could support before collapse became unavoidable. Their original calculation used a simplified picture of neutron matter. Later work added the nuclear force, more complete equations of state, rotation, and observations from real pulsars. The details have changed. The idea remains. A white dwarf has the Chandrasekhar limit, set by electron degeneracy pressure and relativity. A neutron star has a different limit, set by neutron degeneracy pressure, nuclear interactions, and the curvature of space-time itself. It is not a single, easy number written once for every star in every condition. Rotation can give temporary extra support. Heat after a merger can hold matter up briefly. The unknown equation of state shifts the exact value. But for a cold, settled neutron star, nature allows only a limited mass, somewhere around a little more than 2 solar masses, and perhaps not far above that. The final balance begins to fail. The reason is more subtle than ordinary gravity, simply becoming stronger. Gravity does grow with mass. That is familiar. More matter means a stronger inward pull. In Newtonian physics, pressure is only the answer to that pull. Pressure pushes outward. Gravity pulls inward, and a balance can be imagined if the pressure becomes large enough. In that older picture, enough pressure could always seem to save the star. General relativity changes the story. In Einstein's theory, gravity is not produced only by mass in the simple sense. Energy, momentum, and pressure also shape spacetime. Pressure resists collapse, but pressure also contributes to the gravitational field. The very thing holding the star up adds to the thing trying to pull it down. At low compactness, this effect is small. In a neutron star near its maximum mass, it becomes a central part of the problem. As mass is added, the central density rises. The matter responds by producing higher pressure. Neutrons are forced into higher quantum states. Nuclear repulsion becomes stronger at short distances. If the equation of state is stiff, pressure rises sharply and the star resists, becoming smaller. But in general relativity, that pressure is also part of the gravitational source. More pressure means more support, and also more gravity. The balance becomes narrower. At some point, no equilibrium solution remains. The star cannot find a radius where inward curvature and outward pressure match. If the center contracts, the pressure rises, but the gravitational effect of that pressure also rises. The correction overshoots. The support feeds the collapse instead of stopping it. The star has crossed from stable matter into a runaway space-time geometry. This is one of the quiet reversals in compact star physics. Pressure is not always a savior. Under ordinary conditions, it is what prevents collapse. Under the strongest gravity short of a black hole, pressure becomes part of gravity's weight. The defender begins to carry the force of the attack. The star is undone not because the Pauli principle stops existing, and not because the nuclear force turns off, but because their resistance can no longer produce a stable structure in curved spacetime. Observed, neutron stars give the lower edge of the limit. If a pulsar is measured at about 2 solar masses, then the true maximum mass must be above that. The star exists. It pulses. Its companion moves in a way that reveals the mass. Several heavy pulsars have already forced soft equations of state out of the allowed range. Dense matter must be strong enough to support them. A model that collapses at 1.8 solar masses cannot describe the real universe if a 2 solar mass neutron star is seen. The upper edge is harder. A neutron star that crosses the limit does not remain visible for long as a neutron star. It collapses, a black hole may form, and the evidence of the exact threshold is partly hidden behind the horizon. For many years, the range between the heaviest neutron stars and the lightest known stellar black holes was uncertain. Some compact objects seemed missing from that gap. The boundary between matter and black hole was real, but difficult to locate. Then gravitational wave astronomy gave the universe a new way to speak. When 2 neutron stars orbit one another, they lose energy through gravitational radiation. Their orbit slowly shrinks. For a very long time, the change is small. The stars circle in darkness, each one a compact remnant of an older supernova, drawing a little closer with every orbit. Near the end, the motion accelerates. The stars sweep around one another many times each second. Space-time itself begins to ring with their motion. The signal is not sound traveling through air. It is a ripple in the geometry of space-time, stretching and squeezing distances by less than the width of a proton over lengths measured by human instruments. Detectors on Earth register the changing pattern as the stars spiral inward. The waveform rises in frequency and strength, a long, faint chirp from the last moments before contact. In that chirp, the masses are written. So is something more delicate, the way the stars deform under one another's gravity. A neutron star is dense, but it is not perfectly rigid. As 2 of them approach, each raises a tide on the other. The deformation is small compared with the star itself, yet it matters. A stiffer star, with matter that resists compression strongly, may have a larger radius and can be distorted in a different way from a softer, more compact star. This property is called tidal deformability. It is not seen as a picture. It is inferred from the gravitational wave signal, from the way the final orbits differ from the motion of 2 ideal point masses. That is a remarkable kind of measurement. The interior of a neutron star, hidden beneath a crust no probe can enter, leaves a trace in the final spiral of a binary system. Matter at several times, nuclear density changes the timing of space-time ripples that cross the universe. The star's stiffness becomes part of the waveform. Dense matter writes itself into gravity. The event known as GW170817 made this real. 2 neutron stars merged in a galaxy far from the Milky Way, and their gravitational waves reached Earth in August of 2017. The signal was followed by a short burst of gamma rays, and then by light across the electromagnetic spectrum. Telescopes watched the glow fade from blue to red as newly made heavy elements formed and decayed in the expanding debris. It was a merger heard in gravity and seen in light. The two stars had a combined mass of about 2.7 solar masses before losses to gravitational waves and ejected matter. What happened after they touched was brief and revealing. The remnant did not settle into an ordinary long-lived neutron star. Evidence points to a short-lived massive remnant that collapsed into a black hole after losing the temporary support of heat and rapid rotation. That temporary state matters. It shows that a neutron star can be held up for a moment by conditions that cannot last. Rotation can delay collapse. In a merger, the remnant may spin differentially, with different layers rotating at different speeds. Thermal pressure from the violent collision also helps. Magnetic fields and turbulence redistribute angular momentum. Neutrinos carry energy away. The remnant cools. Differential rotation is smoothed. The extra supports fade. If the mass lies above the cold, maximum mass, collapse follows. The star may live for milliseconds, seconds, or perhaps longer in some cases, but not forever. GW170817, therefore pressed on the upper side of the TOV limit. If the remnant collapsed after forming from about 2.7 solar masses, allowing for mass loss to ejecta and radiation, the maximum mass of a cold non-rotating neutron star must be lower than the total starting mass. Combined with the heavy pulsars that set the lower side, the allowed range becomes tighter. The line is still not perfectly drawn, but it is no longer vague. This is how modern astronomy approaches the final mass limit. A heavy pulsar says the limit must be above its mass. A merger remnant says the limit must be below what failed to remain stable. X-ray pulse modeling says how large neutron stars are at given masses. Tidal deformability says how easily they stretch before collision. Nuclear theory says what kinds of matter are possible. Each clue is incomplete alone. Together they press the unknown into a smaller shape. When the line is crossed, the collapse may be quick and comparatively hidden, especially if little surrounding matter remains to shine. The star's surface falls inward. The core contracts. The pressure rises. The added pressure strengthens gravity in the relativistic sense. The runaway begins. Matter that had been held for ages by quantum degeneracy and nuclear repulsion loses its last equilibrium. An event horizon forms when the collapse passes the point from which light can no longer escape. This boundary is not a material shell. It is not a surface floating in space. It is a condition of space-time. Outside it, some paths can still lead outward. Inside it, every future-directed path leads deeper in. Even light has no outward route. The neutron star has crossed from an object that can reveal its surface to a region that can reveal only mass, spin, and perhaps charge. The change is not only a change in density, it is a change in what can be known. A neutron star has layers. It has hotspots. It has a crust that may crack. It has a core whose composition can be debated. It has a radius, a cooling history, a magnetic field, and a pulse. A black hole hides all such interior structure behind the horizon. The outside universe can feel the gravity, measure the spin, and watch matter fall in, but it cannot receive a signal from beneath the boundary. In that sense, the collapse from neutron star to black hole is the loss of a voice. Before collapse, the star can speak through X-rays, radio pulses, glitches, bursts, and gravitational tides. After collapse, the surface is gone. The crust, the superfluid, the possible quark core, the magnetic architecture, all pass beyond direct communication. What remains outside is geometry and gravity. This is why neutron stars hold such a special place. They are the last compact objects with surfaces. They are dense enough for gravity to bend light strongly, but not so dense that light cannot leave. They are relativistic enough to test Einstein's theory, but material enough to test nuclear physics. They sit between the white dwarf and the black hole. Between atoms that still keep their broad structure and space-time, that closes inward completely. The TOV limit is the edge of that middle state. Below it, matter can still answer gravity with pressure. Above it, the answer becomes part of the collapse. The limit is not a failure of quantum mechanics alone or general relativity alone. It is the place where the two meet under conditions so severe that neither can be ignored. Quantum mechanics gives the pressure. General relativity decides how that pressure gravitates. Nuclear physics decides how the pressure grows with density. The star exists only while all three allow balance. A quiet neutron star in the dark may seem permanent. In many cases, it nearly is. Left alone below the limit, it can cool for ages without collapsing. Its heat can fade. Its pulse can weaken. Its magnetic field can decay. The main structure remains. But permanence depends on isolation and mass. Add enough matter. Merge it with another remnant. Push the center beyond what the equation of state can support. Then the old balance ends quickly. Somewhere in a galaxy, two neutron stars may already be spiraling closer. Their pulses, if they beam toward any world, are slowly changing. Their orbit loses energy to gravitational waves too faint to notice until the final stretch. Long before they touch, each star raises a tide on the other, and the shape of dense matter begins to enter the wave. At the end, the stars tear, merge, and decide by mass whether matter remains visible or falls behind a horizon. That decision is one of nature's sharpest transitions. On one side, a neutron star, small, layered, bright in pulses, full of strange matter and measurable signals. On the other side, a black hole. No surface, no pulse from within, no direct message from the matter that crossed inside. The difference may depend on a fraction of a solar mass, on the stiffness of nuclear matter, on rotation that lasts only a moment, on heat that fades almost as soon as it is made. The story began with a massive star running out of fuel. It passed through iron, collapse, neutrinos, a supernova, and the birth of a city-sized remnant. It descended into the Pauli exclusion principle, into neutron degeneracy pressure, into crusts, superfluids, and hidden cores. It followed light as gravity bent it around the star, and waves as merging stars wrote their structure into spacetime. At the end, the answer is calm and severe. A neutron star does not collapse because quantum pressure and nuclear forces can balance gravity, but only below the mass, where relativity permits that balance to exist. Beyond that mass, the star cannot remain a star. The same gravity that shaped it, compressed it, and made it strange takes the final step. The surface disappears. Light loses the path outward. Matter's last structured form gives way to a black hole. Somewhere in the darkness, a pulse stops, and space-time keeps the rest. The neutron star remains far behind now, turning in the dark with its small, hard surface and its hidden core. Its pulses move outward through space, crossing old clouds of gas, passing the faint shells of dead stars, and thinning into the long silence between suns. Nothing in that distance hurries. Light travels. Dust drifts. Gravity keeps its patient hold on worlds that will never know the names given to them. Beyond the remnant, the galaxy opens again. Stars gather in soft bands. Some are young and blue, burning quickly in the places where new clouds have collapsed. Some are old and red, spending their fuel with a slowness that almost feels like rest. Between them lie dark lanes of dust, cold molecular clouds, and the wide spaces where no surface waits, only distance. The universe does not need to explain itself there. It simply continues. The mind can leave the compact star at the edge of its own gravity. Its crust can cool. Its beams can sweep empty regions of space. Its deep interior can keep the quiet pressure of particles that never share the same state. All of that can remain far away, held in the night, while the scene grows wider and softer. The light recedes. The supernova shell becomes a faint haze. The galaxy becomes a pale river. The river becomes one small shape among many others, each one carrying its own stars, its own remnants, its own long histories of fire and cooling. There is no need to follow them further. The journey has already gone deep enough. Only darkness remains around the edges, calm and unbroken. The last image is a point of distant light, steady for a moment, then smaller, then almost gone. Space is quiet again. The body can be still. The room can be still, somewhere beyond sight. The stars continue without asking anything in return.